May 30, 1942. A conference room deep inside the British War Office, Whitehall, London. Admiral Louis Mountbatten stood before a gathering of senior military planners, his words lingering in the air like an absurdity. If ports are unavailable, we may have to build them in sections and tow them into place. The room erupted with laughter. Mockery and disbelief greeted the proposal from men who had spent decades studying naval warfare and military engineering. The notion defied everything the assembled officers understood about harbor construction, physics, and the unforgiving nature of the English Channel. To construct an entire harbor from nothing, transport it across the most dangerous waterway in Europe, and assemble it under enemy fire within days seemed sheer madness. Yet within that moment of ridicule lay the seed of what would become the most audacious engineering achievement of the Second World War, a project so bold it would redefine amphibious warfare and shatter every assumption held by the German High Command about Allied capabilities. The calculations behind D-Day's success were being written not solely in battle plans, but in concrete and steel, in hydraulics and tidal mathematics, in the revolutionary idea that impossibility was simply another engineering challenge awaiting a solution. The catalyst had arrived on August 19, 1942, on the blood-soaked beaches of Dieppe. More than 6,000 Allied troops, primarily Canadian, stormed ashore during Operation Jubilee, a raid intended to test German coastal defenses and demonstrate Allied resolve. The assault descended into catastrophe. German machine guns, entrenched in concrete bunkers atop white chalk cliffs, cut down wave after wave of attackers. 27 Churchill tanks crawled onto the shingle beach, every one destroyed or abandoned. Of the 4,963 Canadians who embarked that morning, only 2,210 returned to England, many wounded. The final casualty figures stunned military planners. Canadian losses alone totaled 3,367, including 916 killed and 1,946 taken prisoner. The Royal Navy suffered 75 dead and 269 missing were captured. The Royal Air Force lost 62 airmen in the skies above Dieppe. German casualties barely exceeded 600. The raid lasted less than 9 hours from first landing to final evacuation. Those 9 hours taught the Allies the costliest lesson of the war. Any future invasion of Fortress Europe would require a major port to sustain operations. Yet Dieppe proved conclusively that a direct assault on a fortified harbor was suicidal. Major General John Hamilton Roberts, commanding the 2nd Canadian Division, wrote in his after-action report rediscovered decades later in the National Archives. The strength of German port defenses exceeded all intelligence estimates. Concrete casemates housing heavy artillery proved resistant to naval bombardment. Machine gun positions enjoyed overlapping fields of fire across every avenue of approach. Port facilities were prepared for demolition at the first sign of attack. Even had we seized Dieppe intact, German counterattacks would have reclaimed it within 48 hours. The strategic paradox became unavoidable. The Allies required a port to invade Europe, yet the Germans had fortified every harbor from Norway to the Spanish border with millions of tons of concrete and steel. Field Marshal Owen Rommel, appointed Inspector General of Atlantic Wall Defenses in late 1943, transformed Hitler's propaganda claims into a genuine obstacle. By December 1943, Rommel had completed a 2-week inspection of Atlantic fortifications. His confidential assessment, preserved in German military archives, revealed deep concern. A coherent defensive concept does not exist, and existing measures do not reflect the seriousness of the impending major landing. His response was characteristically aggressive. Rommel ordered the emplacement of millions of mines along likely invasion beaches. He demanded concrete pillboxes at every key position. He personally oversaw the installation of beach obstacles designed to tear the hulls from landing craft. Rommel's asparagus, tall stakes topped with sharpened points, sprouted across fields behind the beaches to impale gliders and paratroopers. Most critically for Allied planners, Rommel reinforced the ports. In a secret memorandum to Hitler dated December 31, 1943, he wrote, "The focus of the enemy landing will likely be directed against the 15th Army sector. The enemy's primary objective will be the rapid seizure of one or more ports capable of handling large vessels." Hitler designated 11 major ports as Festungen, fortresses to be defended to the last man. Dunkirk, Boulogne, Le Havre, Cherbourg, Saint-Malo, Brest, Lorient, Saint-Nazaire, the Gironde estuary leading to Bordeaux, and the Channel Islands received priority in men and material. Each fortress featured heavy naval guns and reinforced concrete emplacements, artillery covering every approach, extensive minefields, and garrisons prepared to fight to annihilation. German defensive doctrine rested on a foundational assumption no senior commander questioned: an invasion force must seize a major port within days or be defeated by logistical failure. This belief had governed warfare since antiquity. Armies required harbors for supply ships, dockyards for repairs, cranes to unload heavy equipment, warehouses for stores, and shelter from storms capable of scattering an invasion fleet. General Dwight D. Eisenhower, appointed Supreme Commander of the Allied Expeditionary Force, grasped the dilemma with stark clarity. In his personal diary entry from March 1943, he wrote, "We face an impossible choice. Assault a heavily fortified port and suffer catastrophic losses, or land on open beaches and see our supply lines collapse within weeks. Either path leads to defeat. The alternative suggested by failure at Dieppe may be our only hope, though it defies conventional military logic." That alternative had already begun to take shape in the minds of British engineers even before the Dieppe disaster. Its origins dated back to 1917, when Winston Churchill, then First Lord of the Admiralty, proposed using flat-bottomed barges and prefabricated caissons to create an artificial harbor for operations against Dutch coastal islands. The Great War ended before the idea could be tested, but Churchill never abandoned it. In the spring of 1942, weeks before Dieppe, Churchill attended a conference where the impossibility of capturing a port was discussed. His response, recalled years later by multiple participants, electrified the room: "If we cannot capture a port, we shall build one and take it with us." The engineering challenges seemed overwhelming. How do you construct a harbor capable of handling hundreds of cargo ships? How do you transport thousands of tons of concrete and steel across open seas? How do you assemble such a structure under enemy fire? How do you anchor it to a seabed where tides rise and fall 20 feet twice daily? How do you protect it from the violent storms of the English Channel? Each question generated a cascade of technical problems. Yet strategic necessity left no alternative. On May 30, 1942, Churchill issued a directive to Admiral Mountbatten that set the most ambitious construction effort of the war into motion. Preserved in the War Office archives, the directive consisted of 60 words that altered military history. Piers for use on beaches. They must rise and fall with the tide. The anchoring problem must be solved. Present me with the best solution. Do not argue the matter. The difficulties will speak for themselves. Mountbatten assembled a team of Britain's finest engineers, naval architects, and construction specialists. Their initial meetings at the Institution of Civil Engineers on Great George Street in Westminster produced more questions than answers. The sheer scale of what Churchill demanded seemed to violate the laws of physics and common sense. Lieutenant General Frederick Morgan, Chief of Staff to the Supreme Allied Commander, and his Cossack planning team calculated the requirements. The artificial harbors would need capacity equivalent to the Port of Dover, Britain's busiest cross-channel harbor. They must handle 12,000 tons of supplies daily, regardless of weather conditions. They must accommodate ships ranging from small landing craft to Liberty ships of 10,000 tons displacement. They must provide shelter for vessels in seas up to force 6 on the Beaufort scale. They must be assembled and operational within days of the initial invasion. The specifications alone filled hundreds of pages of technical documents. Civil engineer Hugh Iris Hughes, a Welshman with extensive experience in harbor construction, submitted detailed plans for a floating harbor to the Royal Navy between June and August 1942. His design incorporated lessons learned from every harbor project of the previous century. Other engineers contributed specialized components. Royal Engineers Lieutenant Alan Beckett designed flexible steel roadways that could rise and fall with the tides while maintaining continuous connection to the shore. Naval architects proposed using obsolete merchant ships as instant breakwaters by scuttling them in predetermined positions. The most ambitious element involved massive concrete caissons, floating chambers that could be towed across the channel and sunk to form breakwaters. In October 1942, a combined operations conference named Rattle took place at Lars Inn, Scotland. There, Commodore John Hughes Howlett and Royal Navy Captain Tom Hussey presented the complete scheme to assembled military planners. The presentation lasted 4 hours and covered every technical aspect from tidal calculations to concrete mixing ratios. Skepticism dominated the initial reaction. American officers on the planning staff expressed particular doubt. One U.S. Navy captain, whose name appears in the conference minutes only as Captain S., voiced the consensus concern. "You're proposing to construct the equivalent of Dover Harbor, dismantle it into thousands of pieces, transport those pieces across the most dangerous waterway in the world, reassemble them under enemy artillery fire, and have the whole thing operational within a week." Gentlemen, I've been in the Navy for 25 years, and this is the most preposterous scheme I've ever encountered. Hughes Howlett's response, recorded verbatim in the conference transcript, demonstrated the desperation driving Allied planning. Captain, you're absolutely correct. This scheme is preposterous. It defies every principle of harbor engineering. It requires technical innovations that don't yet exist. It demands industrial production on a scale that may exceed our capacity. Yet, I ask you to consider the alternative. We either solve these preposterous problems or we abandon any hope of invading Europe. The choice is that simple. A demonstration helped convince the skeptics. Commander Robert Grant conducted an impromptu experiment using the conference room sink, paper model ships, and a hairbrush to create waves. First, he placed the paper fleet in the sink and vigorously brushed the water. The paper ships capsized immediately. Then Grant inflated a Mae West lifebelt and placed it in the sink to represent a breakwater. The paper fleet sat inside the protected area. Again, he applied the brush vigorously, creating waves that broke against the lifebelt. The paper ships remained afloat. The demonstration was crude, almost childish, yet it illustrated a fundamental truth. Protected water meant surviving ships. Surviving ships meant sustained supply. Sustained supply meant victory. The proposal went to Quebec in August 1943, where Churchill and President Franklin D. Roosevelt met with the combined chiefs of staff. Churchill presented the artificial harbor concept with characteristic eloquence. His opening statement, preserved in the conference minutes, captured the audacity of the plan. Gentlemen, we propose to undertake the greatest construction project in military history, and to do so in complete secrecy at breakneck speed. Under constant threat of enemy detection, we will build 2 complete harbors, transport them across the Channel, and assemble them on hostile shores. The Germans will not believe such a thing possible. Their disbelief will be our greatest weapon. Roosevelt understood immediately. His engineering background, dating to his time as Assistant Secretary of the Navy, gave him appreciation for the technical challenges. Yet, he also grasped the strategic necessity. The Joint Chiefs of Staff debated for 2 days. They examined every aspect of the plan, from concrete strength requirements to tidal predictions to German coastal artillery ranges. Finally, on September 2, 1943, they issued their decision. The combined chiefs of staff estimated that the artificial ports would need to handle 12,000 tons per day, exclusive of motor transport and in all weathers. On September 4, the go-ahead was given to start work immediately on the harbors. Infighting between the War Office and the Admiralty over responsibility threatened to derail the project before construction even began. The Admiralty wanted complete control, arguing that anything floating fell under naval jurisdiction. The War Office countered that harbor construction was fundamentally an Army engineering responsibility. The dispute raged for 3 months, consuming countless planning meetings and delaying critical decisions. Only on December 15, 1943 did the Vice Chiefs of Staff intervene to impose a solution. The Admiralty would manage the block ships to be scuttled as breakwaters, the bombarded or floating outer breakwaters, and all assembly work on England's south coast. They would also survey the French coast, mark navigation channels, and tow all components across the channel. The War Office would construct the concrete caissons sea-named Phoenix, the floating roadways sea-named Whale, and provide anti-aircraft protection. Once in France, the Army would sink the caissons and assemble the complete harbor. The division of labor established, construction could finally begin. The scale of the project dwarfed anything Britain had attempted. From the summer of 1943, construction began in earnest, employing up to 45,000 personnel simultaneously across dozens of sites. The concrete caissons alone represented an engineering marvel. The largest Phoenix units measured 200 feet long, 60 feet high, and weighed more than 6,000 tons when complete. A total of 213 caissons of various sizes would be required, consuming more than 1 million tons of reinforced concrete and 70,000 tons of steel reinforcement. Massive excavations were carved from the banks of the Thames and Medway rivers to create the dry docks where Phoenix units could be built. The construction process required precision that seemed impossible given the urgency. Each caisson was essentially a floating concrete box, airtight except for controlled flooding valves that would lower it to the seabed in precise positions. The walls had to be thick enough to withstand Atlantic storms, yet light enough to float during transport. Reinforcing steel had to be positioned with mathematical exactness to prevent structural failure. Concrete had to be mixed, poured, and cured under controlled conditions despite chronic wartime shortages of cement and steel. Commercial construction firms across Britain received contracts for individual caissons. Warts Construction, Baffer Batty, Henry Boot, Bovis and Company, Costain, John Lang and Son, Peter Lind and Company, Sir Robert McAlpine, Mullum, Nuttall and Taylor, Woodrow, all contributed sections. The firms worked in ignorance of the final purpose. Security demanded that construction workers know only their immediate task, not the grand design. Arthur Warts, managing director of Warts Construction, would recall decades later in a 1970 interview, "Our workers built massive concrete pontoons according to specifications provided by government engineers. We had no idea what they were." 4. The rumor circulating among the men was that these were somehow related to post-war housing construction. When a senior officer from Whitehall visited our yards and saw how puzzled everyone looked, he reassured us that our work was vitally important for the war effort. Only after D-Day did we learn we'd been building sections of artificial harbors. The floating roadways presented equally daunting challenges. Alan Beckett's design called for steel bridge spans 80 feet long mounted on floating pontoons made of either steel or concrete called beetles. The bridges had to be flexible enough to accommodate tidal variations of up to 20 foot while rigid enough to support fully loaded trucks. The solution involved a torsionally flexible joint system that allowed each span to twist independently while maintaining continuous roadway surface. 16 kilometers of these whale roadways would be manufactured, each section precisely engineered to connect with its neighbors. The pier heads where ships would actually dock received the code name Spud. Each consisted of a massive pontoon with 4 legs that rested on the seabed while the pontoon floated up and down with the tides. Hydraulic systems allowed the legs to extend or retract as tidal conditions changed, maintaining constant deck height relative to docked ships. The engineering tolerances were measured in fractions of an inch over structures weighing hundreds of tons. Testing became crucial. The Scottish harbor at Garriston and Wigton Bay offered characteristics similar to the Normandy beaches. Flat, sandy, remote, and sparsely populated, it provided perfect conditions for full-scale trials. A security cordon was established around the entire area. Local inhabitants were evacuated under wartime emergency powers. The whole area, from Garriston through to the Isle of Thorn, was declared off-limits. A military camp was constructed at Cad to accommodate hundreds of engineers and support workers who would test and refine the Mulberry components. The tests revealed numerous problems that would have proven catastrophic if discovered only on D-Day. Early floating roadway designs collapsed under the weight of a 7-ton truck when subjected to realistic wave action. Swiss roll type flexible roads washed away entirely during a storm that hit the test site. Hippo pontoons undermined in the sandy bottom, causing crocodile bridge spans to fail structurally. Only Beckett's whale design survived the storm undamaged, leading to its adoption for the final harbor. The bombardons, massive floating breakwaters fabricated from steel and rubberized canvas, underwent extensive modification after test failures. Original designs called for hemp rope connections between individual bombarded units. Testing showed the ropes parted under storm conditions, allowing the huge structures to drift into the inner harbor, where they could cause catastrophic damage. New steel cable connections with redundant safety systems replaced the rope after repeated test failures. Security surrounding the project approached paranoia. The code name Mulberry was selected specifically because it revealed nothing about the project's nature. It was simply the next available designation in a long list of randomly selected code names. All written communications referred only to Mulberry, never to artificial harbors or floating ports. Workers at construction sites signed Official Secrets Act declarations. Photographs of the components were strictly forbidden. Intelligence services monitored conversations in pubs near construction yards, alert for any Loose talk, German aerial reconnaissance posed a constant threat. Luftwaffe. Planes photographed southern England regularly, searching for evidence of invasion preparations. The Phoenix caissons proved impossible to hide once construction began, as they were simply too large. The cover story claimed they were experimental anti-submarine barriers to be deployed in the English Channel. German intelligence apparently accepted this explanation as no special preparations were made to counter artificial harbors. An extraordinary security breach nearly exposed the entire project. In May 1944, just weeks before D-Day, the Daily Telegraph crossword puzzle began, including words directly related to Operation Overlord. On consecutive days, clues led to solutions, including Utah, Omaha, Juneau, Sword, Gold, the names of the 5 invasion beaches, and most alarmingly, Mulberry itself. MI5 immediately investigated Leonard Dorr, the headmaster who compiled the Telegraph crossword. Intensive interrogation revealed that Dorr often asked students for interesting words to include in his puzzles. Many of those students lived near U.S. military barracks where Overlord planning was underway. The words had entered Dorr's vocabulary through casual conversation overheard by students and repeated innocently. MI5 concluded the appearance of classified operation names was indeed coincidence, though an unnerving one. The investigation continued until after D-Day to ensure Dorr wasn't a German agent using an impossibly subtle communications method. By June 1944, the artificial harbors existed as thousands of individual components scattered across southern England. The logistics of moving them to assembly points, then across the channel, then into final position off the Norman coast boggled the mind. 2 complete harbors had been constructed. Mulberry A would support American forces landing at Omaha Beach, near San Lawrence. Mulberry B, also called Port Winston in honor of Churchill, would support British and Canadian forces at Gold Beach near Aramanes. Each harbor required approximately 600,000 tons of concrete and prefabricated steel. The components included 213 Phoenix caissons of various sizes, 10 miles of whale-floating roadways, 33 pier heads, 70 obsolete merchant ships to be scuttled as additional breakwaters in positions C-named gooseberries, and 24 massive bombard floating breakwaters for outer protection. Moving this artificial fleet required 150 ocean-going tugs, specially modified for long distance towing. The tugs were distinguished by large M letters painted on their funnels. Crews took fierce pride in their assignment, understanding they were part of history's most ambitious engineering project. The towing operations alone presented staggering complexity. Phoenix caissons had to be towed at speeds not exceeding 4 knots to prevent structural damage. The journey from English assembly points to the Normandy coast would take 2 days under ideal conditions. Weather predictions became crucial. Rough seas could damage delicate components or part the tow cables. The tugs had to navigate mine-infested waters while maintaining station in massive convoys. Royal Navy minesweepers worked ahead of the Mulberry convoys, clearing lanes through defensive minefields laid months earlier. June 4, 1944 brought the first movement orders. Sections of the Mulberry Harbors began to be towed behind tugs and positioned mid-channel, awaiting the invasion that had been scheduled for June 5. Then weather intervened. A massive storm system swept across the channel, forcing postponement. The Mulberry components wallowed in rough seas for 24 hours while Eisenhower agonized over whether to proceed or delay further. When Eisenhower finally gave the order to launch Overlord on June 6, the artificial harbor components were already at sea. In the pre-dawn hours of D-Day, while Allied soldiers stormed ashore under withering German fire, the first elements of the Mulberry Harbors were being towed into position. The operation proceeded with choreographed precision despite the chaos of the largest amphibious assault in history. On D+1, June 7, the first Phoenix caissons were brought into position about a mile offshore from both Omaha and Gold Beaches. Powerful harbor tugs maneuvered the massive concrete structures with remarkable delicacy, nudging them into precise positions marked by buoys laid down by Royal Navy survey ships days earlier. The controlled flooding of the Phoenix caissons demonstrated the brilliance of their design. Each caisson had multiple chambers with individual Flood valves. Engineers could flood specific chambers to achieve exact positioning and orientation before settling the structure to the seabed. The process required hours of careful work for each caisson, but the results justified the effort. As the Phoenix breakwater took shape, it created sheltered water where ships could anchor safely. Simultaneously, 70 obsolete merchant ships moved into position for scuttling. These vessels, sea-named corn cobs and collectively creating the Gooseberry Breakwaters, had been assembled at Oan on Scotland's west coast months earlier. Stripped of everything valuable, ballasted for precise buoyancy, and fitted with scuttling charges, they made their final voyage under their own steam. At predetermined coordinates off the invasion beaches, the crews opened seaocks, detonated charges, and abandoned ship. The vessels settled to the bottom in carefully planned positions, creating an outer line of protection against the Atlantic swells. At Utah Beach, 10 ships went down, including the Benjamin Conti, David O. Sailor, George S. Son, and Victory Sword. At Omaha Beach, another formation of corncobs established the outer perimeter of Mulberry. The scuttling operations proceeded so smoothly that most ships settled within 5 feet of their assigned positions, a remarkable achievement given the complexity of deliberately sinking a ship exactly where intended. The whale roadways came next. Long trains of linked pontoons and bridge spans snaked across the channel, towed by dedicated tugboats. Once in position, Royal Engineers secured them to the spud pier heads and extended them toward shore. The flexible joints that Beckett had designed proved their worth as the roadways undulated with the waves while maintaining structural integrity. By June 13, Mulberry B at Aramains had developed sufficiently to provide 2 crescent-shaped harbors capable of accommodating up to 75 Liberty ships and smaller craft simultaneously. The speed of construction astonished even the engineers who had planned it. Within just 7 days of the D-Day landings, both artificial harbors were beginning to handle cargo. The first supply ships to use the Mulberry facilities found themselves in the strange situation of docking at piers that hadn't existed 10 days earlier in harbors built from materials that had been scattered across England 2 weeks before. Ship captains accustomed to traditional harbors marveled at the ingenuity. Captain James Morrison of the Liberty ship Robert E. Perry I wrote in his ship's log, approached what the charts show as open beach, instead found complete harbor facilities, including floating piers, breakwaters, and navigational markers. Docked at Pier 7 of Aramancha's harbor, and discharged 400 tons of ammunition, 200 tons of rations, and 150 vehicles in 8 hours. The entire facility floats on the tide, rising and falling 15 feet between high and low water, yet remains perfectly functional throughout. The engineering involved defies my comprehension. Then disaster struck. On June 19, 1944, the worst June storm in 40 years descended on the English Channel. For 3 days, northeasterly winds of force 6 to force 8 pounded the Normandy coast. Waves reaching 8 feet in height crashed against the artificial harbors. The bombard and outer breakwaters designed to absorb such punishment began to fail. Some broke apart under the pounding. Others tore free from their anchors and drifted into the inner harbors where they smashed into Phoenix caissons and whale roadways. At Omaha Beach, Mulberry suffered catastrophic damage. The harbor had not been fully completed when the storm arrived. Critical reinforcements and anchor systems were still being installed. Phoenix caissons cracked under the wave assault. Whale roadways broke free and washed onto the beach in tangled wreckage. By the time the storm abated on June 22, Mulberry was beyond repair. The American decision to abandon Mulberry came quickly. Surveys showed that restoring the harbor would take longer than building it originally, as damaged components would first need to be removed. Instead, the Americans salvaged usable sections and sent them to reinforce Mulberry B at Aramains. The British harbor, more protected by the natural geography of Gold Beach and more completely assembled before the storm, survived with damage but remained functional. Mulberry B was substantially reinforced with units salvaged from the American harbor. The Phoenix caissons were pumped full of sand to give them greater stability, a measure that undoubtedly explained the extended service which the British port rendered. The storm validated the Mulberry concept, even as it destroyed one of the harbors At Omaha Beach, where Mulberry lay in ruins, the gooseberry breakwater created by scuttled ships had held firm. Ships, anchoring in the protected water behind the blocked ships, rode out the storm with minimal damage. Without even that basic protection, the June storm would have scattered the invasion fleet and potentially doomed the entire operation. Lieutenant Colonel George Shattuck, commanding 20 Port Group Royal Engineers responsible for operating Mulberry B, wrote in his after-action report, "The storm of June 19 to 22 subjected our harbor to conditions far exceeding design specifications. That any portion survived testifies to the quality of British engineering and the foresight of our planners. The bombarded which failed did so while absorbing punishment that would have destroyed the entire invasion fleet had those ships been exposed to open water. Even in failure, the Mulberry concept proved its value. The loss of Mulberry A forced the Americans to rely on direct beach landing of supplies, a technique they refined to unexpected levels of efficiency. By early July, Omaha Beach was handling 12,000 tons daily despite lacking a harbor. An achievement that surprised everyone, including the planners. Yet, this success depended on the gooseberry breakwater, a Mulberry component. Mulberry B at Arromanches continued operating long past its design life. The harbor was intended to function for just 3 months, sufficient time to capture and restore the port of Cherbourg. Instead, Port Winston remained operational for 10 months after D-Day. The statistics of what this single artificial harbor accomplished defied belief. Through Port Winston passed 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. At peak efficiency, the harbor was landing 7,000 tons of equipment and supplies daily. The port operated around the clock with ships docking at any hour to discharge cargo. The whale roadways proved their worth beyond anyone's expectations. Designed for a 3-month lifespan, they handled traffic constantly for 10 months. Fully loaded trucks drove from Liberty ships anchored offshore directly onto French soil across bridges that floated on the tide. Many of these bridge spans found second lives after the war, repaired and used to replace bombed bridges across France, Belgium, and the Netherlands. Examples remain visible to this day, including a span over the Noro River in Normandy and another crossing the Mosel River between Cattenom and Königsmacke. The German reaction to the Mulberry harbors revealed the complete failure of their military intelligence and strategic thinking. German commanders had based their entire defensive strategy on the assumption that the Allies would need to capture a port. RML had fortified Cherbourg, Le Havre, and other harbors precisely because he believed invasion forces could not survive without them. The Atlantic Wall with its millions of mines and thousands of concrete bunkers was positioned primarily around port facilities. When Allied forces came ashore on beaches rather than ports, German intelligence initially interpreted this as evidence of a limited raid rather than a full invasion. Even when the scale of the landings became apparent, German commanders assumed the Allies would rapidly move to capture Cherbourg. The appearance of artificial harbors off the invasion beaches shocked the German high command. They had no intelligence warning of the Mulberry project despite its massive scope. The concept violated German assumptions about what was militarily possible. Their disbelief bought the Allies precious time to consolidate the beachhead. Albert Speer, Nazi Germany's Minister of Armaments and War Production, would later provide the most eloquent testament to the Mulberry Harbor's impact. After the war, during interrogation, and later in his memoirs, Speer reflected on the Atlantic Wall's failure. His words, though coming from an architect of Nazi war crimes, captured the essence of why Germany lost. To construct our defenses in 2 years, we used 17 million km of concrete and 1.2 million tons of steel. A fortnight after the landings by the enemy, this costly effort was brought to naught by an idea of simple genius. The simple genius Speer referenced was the Mulberry concept. Germany had invested enormous resources into fortifying every port along the Atlantic coast. The Nazi High Command believed these fortifications made invasion impossible without catastrophic Allied casualties. Instead, the Allies simply bypassed the fortified ports entirely, bringing their own harbors with them. This represented more than a Tactical surprise. It demonstrated a fundamental difference in how the two sides approached warfare. German military thinking remained rooted in 19th century concepts of fortress warfare and defense of strongpoints. The Allies embraced innovation, willing to attempt solutions that conventional wisdom deemed impossible. The contrast extended beyond the Mulberry Harbors to encompass Allied strategy as a whole. While Germany relied on static defenses and counterattacks with armored reserves, the Allies developed specialized equipment to overcome obstacles. Hobart's Funnies, a collection of modified tanks, including flail tanks for clearing mines, bridge-laying tanks for crossing obstacles, and amphibious tanks for swimming ashore, epitomized this innovative approach. The Germans had technical brilliance as evidenced by weapons like the V-2 rocket and jet aircraft, but they lacked the industrial capacity and strategic flexibility to turn technical innovations into war-winning advantages. The Allies, particularly the United States and Britain working together, combined innovation with industrial mass production. The Mulberry Harbors exemplified this combination. The engineering innovations. From Beckett's flexible roadways to the Phoenix caissons controlled flooding systems represented cutting-edge design. Yet the project succeeded because British industry could manufacture these innovations in quantity despite 4 years of total war. Over 45,000 workers contributed to Mulberry construction simultaneously. Commercial firms across Britain diverted resources from other war work to produce components. The scale of coordination required dozens of government ministries, military services, and private companies to work in unprecedented cooperation. This organizational achievement matched the technical accomplishment. Consider the Phoenix caissons alone. Building 213, massive reinforced concrete structures, each weighing thousands of tons, required more concrete than most nations produced in an entire year. The construction sites had to be created from scratch along river banks. Raw materials, cement, steel, aggregates had to be allocated despite desperate shortages. Transport to assembly points required specialized equipment and careful scheduling. Quality control had to ensure every caisson could survive ocean towing and storm conditions. The towing operation itself deserves recognition as a maritime achievement, moving 600,000 tons of concrete and steel across 30 miles of open water while maintaining precise positioning and timing stretched naval capabilities to their limits. The 150 tugs involved in Operation Mulberry represented a significant portion of Britain's entire tug fleet. Many were commercial vessels pressed into military service. Crews received minimal training on towing oversized loads through minefields and enemy-controlled waters, yet the loss rate during the cross-channel towing operations remained remarkably low. Only a handful of Phoenix caissons were lost during transport, and most of those were damaged in the June storm rather than during the actual channel crossing. The human side of the Mulberry story deserves equal attention with the technical achievements. Colonel V.C. Steer Webster, a royal engineer who played a leading role in the invention, design, development, and trials of all Mulberry equipment, left behind an extensive archive now housed at McMaster University in Canada. His papers reveal the intense pressure engineers worked under as D-Day approached. Steer Webster's diary entries from March through May 1944 document the frantic pace. March 15, 1944. Churchill visited the whale testing facility today. He wanted to personally walk across the floating roadway to satisfy himself it would support loaded trucks. After watching vehicles cross successfully, he turned to me and said, "Steer Webster, if this damned thing works as well in France as it does here in England, you chaps will have earned the nation's eternal gratitude." The immense weight of responsibility we carry becomes more real with each passing day. April 3, 1944. Received word that 2 Phoenix caissons developed cracks during towing trials. Immediate investigation reveals the reinforcing steel was improperly positioned at the construction yard. All similar units must now be inspected. This delay could push back the entire invasion if we cannot resolve it within a week. Sleep has become a rare luxury. May 20, 1944. Final preparations underway. The sheer scale of what we've built staggers belief. If someone had proposed this scheme to me 3 years ago, I would have declared it impossible. Yet here we stand, having turned impossibility into imminent reality. God help us all if it fails. The personal accounts from royal engineers who operated the Mulberry Harbors in France provide ground-level perspective on the achievement. Sapper William Hutchinson, attached to 20 Port Group, wrote to his family in July 1944, "We work 18-hour days keeping Port Winston operational. The harbor lives and breathes like a great mechanical beast. With each tide the entire structure rises 15 feet and falls again. We must constantly adjust moorings, inspect pontoons for damage, repair roadway sections, and guide ships to pier heads. German artillery occasionally shells us from inland positions. Luftwaffe raids occur nightly. Yet the supplies flow without pause. Today alone, we unloaded 40 ships, carrying tanks, ammunition, rations, fuel, and medical supplies. Everything an army needs arrives through our floating harbor. When I think that this entire port didn't exist a month ago, that we assembled it under fire from components towed across the channel, I can scarcely believe I'm part of it." Merchant Navy crews delivering supplies through Port Winston expressed amazement at the facility. Captain Robert Fraser, master of the Liberty ship John P. Holland, filed a report with his shipping company after his third voyage to Arromanches, approached the French coast expecting to anchor offshore and lighter cargo to the beach in small craft. The standard procedure for unimproved harbors instead received orders to proceed directly to Pier 11 in Port Winston. The entire harbor, consisting of breakwaters, floating piers, and navigational aids, appeared as substantial as any permanent installation I've docked it in 20 years at sea. The engineering required to construct this facility from scratch, anchor it against channel tides and storms, and maintain it under combat conditions represents an accomplishment that will be studied for generations. We offloaded 500 tons in 6 hours and departed to make room for the next vessel. The efficiency matched peacetime operations at established harbors. The influence of the Mulberry Harbors on the Normandy campaign's success cannot be overstated. Without them, the Allies faced three grim options. First, suffer massive losses capturing a fortified port like Cherbourg immediately after D-Day when forces were weakest and German opposition strongest. Second, rely entirely on beach landings for supplies, leaving the invasion fleet vulnerable to storms, as the June tempest demonstrated. Third, postpone the invasion indefinitely while searching for an uncertain alternative. The Mulberry solution removed these impossible dilemmas. It provided the Allies with harbor capacity equivalent to a major port without the casualties of assault or the exposure of open beaches. The harbors managed sufficient tonnage to sustain the buildup of forces in Normandy during the crucial initial months. By the time Cherbourg fell to American troops on June 26, 1944, the immediate crisis had been resolved. The Allies had secured an unshakable foothold in France. Even when German demolitions rendered Cherbourg unusable for weeks, the advance continued because Port Winston maintained the supply flow. The strategic ramifications extended beyond Normandy. The success of the Mulberry Harbors fundamentally reshaped Allied amphibious doctrine. After D-Day, planners no longer assumed they needed to seize a port immediately. Future landings could touch down on any suitable beach, confident that artificial harbor methods could sustain operations until permanent ports were captured and restored. This flexibility granted the Allies enormous advantages in selecting landing sites. They could prioritize beaches based on weak defenses rather than proximity to ports. German commanders could no longer concentrate defenses around key harbors, knowing the Allies might strike anywhere along thousands of miles of coastline. This paranoia forced Germany to disperse forces, rather than amass them at decisive points. Plans were drafted to use Mulberry technology for a future invasion of Japan. Engineers were sent to the Pacific Theater to survey potential landing sites and assess construction needs. The atomic bombings of Hiroshima and Nagasaki in August 1945 made these plans unnecessary, but the preparation demonstrated how thoroughly the Mulberry concept had been institutionalized as standard Allied procedure. No comparable wartime engineering feat has been attempted since 1944. The integration of technical innovation, industrial-scale production, security, logistics, and operational deployment under fire remains unparalleled in military history. Modern militaries studying amphibious operations still examine the Mulberry Harbors as a model for solving seemingly impossible challenges through engineering ingenuity. Physical remnants of Port Winston survive today at Arromanches. Phoenix caissons, still visible at low tide, mark the outer breakwater. Local fishermen use them as navigational landmarks. Tourists visiting the D-Day beaches can observe the concrete evidence of Allied engineers' accomplishments in 1944. Several Phoenix caissons dot the British coastline as well, testaments to construction experiments and failures. At Pagham Harbour in West Sussex, a caisson known as the Near Mulberry sank during towing and could not be refloated, now scheduled as a protected historic site. Another caisson, the Far Mulberry, fractured in a storm the night before D-Day and rests in deeper water offshore. At Thorpe Bay near Southend, a phoenix being towed from Immingham began leaking and was intentionally beached on a sandbank in the Thames estuary. It also gained protected monument status, accessible at low tide for those willing to wade through mud to examine its construction. These failures, preserved as accidental monuments, remind us that the Mulberry project carried substantial risk. Not every component functioned as designed, and not every caisson reached France intact. The June storm destroyed one complete harbor and damaged the other. Yet the project succeeded because British and American engineers built redundancy into the system, devised multiple solutions for critical issues, and adapted quickly when initial designs failed. The long-term influence of the Mulberry Harbors on civil engineering is notable. Innovations developed for military necessity found peacetime applications. Floating bridge technology advanced significantly due to Beckett's whale roadway design. Post-war harbor construction incorporated lessons learned about breakwater design and tidal accommodation. Concrete mixing and curing techniques developed to produce phoenix caissons under wartime pressure improved commercial construction practices. Most importantly, the Mulberry project demonstrated that massive engineering undertakings could be completed in months rather than years when urgency demanded. The organization, planning, and execution skills developed during Mulberry construction influenced post-war infrastructure projects worldwide. Personnel involved in building the artificial harbors later entered commercial construction, bringing experience in managing complex projects under strict constraints. Recognition for Mulberry engineers arrived gradually. Wartime secrecy kept details classified for years after 1945. The engineers themselves, modest by nature, rarely sought publicity. Steer Webster's archive remained private until donated to McMaster University in 1976. Hugh I. Orris Hughes received no public accolades during his lifetime despite his vital contributions. Alan Beckett, whose whale roadways proved essential, continued his engineering career in relative obscurity. Only decades later did historians recognize the scale of achievement represented by the artificial harbors. The institution of civil engineers included the Mulberry Harbors among the 200 projects celebrated during its 200th anniversary in 2018. Scholarly studies analyzed the technical and organizational aspects of the project, while documentaries brought the story to wider audiences. Military historians acknowledged that D-Day's success depended as much on engineering innovation as on military valor. The contrast between Allied and German approaches to the invasion problem crystallized in the Mulberry Harbors. Germany chose the obvious solution: fortify existing ports so heavily that capture was nearly impossible. The Atlantic Wall, with millions of tons of concrete and elaborate defensive systems, exemplified conventional military thinking executed with German thoroughness. The Allies chose the unobvious solution: make ports irrelevant by creating new ones wherever needed. This required believing the impossible could become possible through engineering and industrial effort. It required leaders willing to authorize enormous expenditures on an untested concept, engineers willing to attempt what conventional training said could not be done, and construction workers laboring in ignorance to build components they did not fully understand for purposes they could not yet envision. This difference in mindset explains why the Allies triumphed. German military culture valued obedience, hierarchy, and adherence to proven methods. This produced excellence in execution but rigidity in planning. When Allied actions violated German assumptions, the command structure struggled to adapt. Allied military culture, particularly Anglo-American cooperation, valued innovation, flexibility, and pragmatic problem-solving. This sometimes produced chaos and inefficiency, but it allowed rapid adaptation to changing circumstances. When conventional solutions proved inadequate, the Allies sought unconventional alternatives. The Mulberry Harbors embodied this cultural advantage. German general confronted with the harbor problem would have calculated forces needed to capture Cherbourg and accepted the casualties. An Allied general authorized the creation of floating ports to bypass the problem entirely. On the 40th anniversary of D-Day in 1984, surviving Mulberry engineers gathered at Arromanches to reflect on their achievement. The reunion included British and American participants, military and civilian contributors, designers, and construction workers. Their recollections, recorded by the Imperial War Museum, provide a fitting conclusion to the Mulberry story. Sir Bruce White, who oversaw much of the construction, spoke at the reunion dinner. "We were young men facing an impossible task. Build a harbor that could be assembled in days, that could float yet withstand Atlantic storms, that could handle more cargo than expected while anchored to sand rather than bedrock. Every engineering principle we'd learned said it couldn't be done, yet we had no choice. The invasion depended on solving these impossible problems. We stopped asking why it couldn't work and focused on making it work. We tested, failed, modified, and tested again. We manufactured on a scale that strained Britain's industrial capacity. We towed floating concrete boxes across mined waters. We assembled harbor components while German artillery shells fell around us. And it worked. Not perfectly. Mulberry was lost in the June storm, many components failed. Constant repairs were needed, but it worked well enough. Port Winston kept the supplies flowing. That time made the difference between victory and defeat. Alan Beckett, whose whale roadways were critical, reflected. I was a young lieutenant in the Royal Engineers tasked with solving the floating roadway problem. The requirements seemed contradictory: must flex for 15 feet tidal variations, must support loaded lorries, must survive months in saltwater, must be simple to manufacture, must be transportable across the channel. Each requirement alone was challenging. Together, they seemed impossible. I spent weeks sketching, building models, testing in a lab. The breakthrough came from observing a snake moving across sand, rigid within spans but flexible at joints. That torsional flexibility became the key innovation. Once established, detailed engineering followed. Seeing the whale roadways still functioning at Arromanches 10 months after D-Day, handling far more traffic than designed, gave me greater satisfaction than any other engineering work. An American engineer who worked on the Phoenix caissons added, "People focus on the technical innovations, and rightly so, but the manufacturing process deserves equal recognition. We built 213 massive reinforced concrete structures in 8 months while Britain fought a total war. Every resource, cement, steel, timber, labor, transport, was needed elsewhere. Yet the Mulberry Project received what it needed because Churchill and Eisenhower understood its importance. Coordination was staggering. Concrete had to meet precise specifications, steel positioned within millimeter tolerances, caissons built in dry docks, floated out, towed, and positioned precisely, all while maintaining secrecy under nightly raids. From the humblest laborer to the senior engineer, everyone understood they were creating something historic. The Mulberry Harbors stand as a testament to human ingenuity, the power of innovation over conventional thinking, and the triumph of flexible problem-solving over rigid doctrine. When faced with a strategic challenge seemingly without solution, Allied planners asked how engineering could create an answer that changed warfare itself. The artificial harbors of Normandy epitomized the arsenal of democracy, the union of technical innovation and industrial capacity that defined Allied victory in the Second World War. More than battles, heroism, or tactics, it was this willingness to attempt the impossible and make it real that determined the outcome. The Germans fortified what existed, the Allies created what was needed.